Hello and welcome to this webinar where we will talk about wireless power transfer systems from problem to practical solutions. In this webinar, first we will slightly talk about the fundamentals and key factors of WPT systems, and then we will have a live demo on simulating a wireless power charger in electrical vehicles using the EMWorks EMAG finite element software. If you have any question during this webinar, feel free to ask in the chat box or comment section, and I will answer them all after the live demo. Let's see what we will learn in this webinar. First, we will talk about why wireless power transfer matters, and then we will see how wireless power transfer works. After that, we will talk about key factors on WPT operation, and then we will start a simulation in action in the live demo. The last part will be question and answer to share our experiences in this field. Wireless power transfer systems allow energy to move from a transmitter coil to a receiver coil without any physical contact. In this slide, we want to explain why wireless power transfer is important and why it deserves our study. Traditional wired power connections face several limitations that make them less suitable for future technologies. Physical contacts are vulnerable to friction, vibration, moisture, and corrosion, which eventually lead to mechanical failure. Cables and plugs also require frequent replacement, especially in harsh or industrial environments, resulting in high maintenance needs. In addition, wired connections restrict mobility and prevent the design of fully sealed, waterproof, or rotating systems. This creates significant design limitations. Moreover, exposed metal contacts can generate sparks or create electrical hazards, particularly in the medical devices or industrial machines. Because of these challenges, wireless power transfer provides a more reliable, durable, and safer alternative for next-generation systems. Now let's talk about why wireless power transfer matters. Because of its benefits, wireless power transfer offers several important advantages for modern power delivery. First, there is no physical contact, so there is no mechanical wear and the system lasts much longer. It also provides safe and reliable operation since there is no exposed metal connectors that can cause spark or electrical hazards. Another key benefit is that WPT enables compact and fully sealed designs, which is essential for medical devices and underwater systems and harsh environments. Finally, wireless power is highly flexible and can be used in many applications such as electric vehicle charging, robotics, and other systems that require mobility or rotation. In this slide, we explain how a wireless power transfer system works. A WPT system has two main parts, a transmitter coil and a receiver coil. The AC source drives the transmitter coil and generates an alternating magnetic field. This changing magnetic field links to the receiver coil and, based on Faraday's law, it induces a voltage or EMF in it. To improve efficiency, both coils are usually tuned to the same resonant frequency, which strengthens the magnetic coupling between them. Once the voltage is induced, the receiver coil can deliver power to the load, either directly or through a simple power conditioning circuit. Overall, the strength of power transfer depends on factors like coil distance, alignment, and coil geometry. In a wireless power transfer system, there is always a physical gap between the transmitter or TX and receiver or RX coils. Because of this distance, Not all of the magnetic flux can be coupled to the receiver, which creates leakage inductance. This leakage inductance causes reactive power to circulate in the system instead of delivering useful power to the load, leading to low energy transfer efficiency. To solve this problem, a compensation circuit is added to the system. By using capacitors arranged in the series or parallel, the circuit is tuned to resonance, which cancels the reactive power, improve the power factor, and significantly increase the overall transfer efficiency. One of the most important parameters in the wireless power transfer is the coupling coefficient, which shows how effectively the magnetic flux from the transmitter coil links to the receiver coil. As the distance between the coils increases, the magnetic flux linkage becomes weaker. This reduces the coupling coefficient, and as a result, less power is transferred. As can be seen in the distance plot in this slide, the coupling decreases as the separation grows. Horizontal misalignment also significantly reduces the coupling coefficient. When the coils are not properly aligned, their overlapping area decreases, leading to uneven magnetic field interaction and reduced power transfer. This effect is also illustrated here in this slide. In a wireless power transfer system, both the load and the distance between the coils have a strong effect on the power delivered and overall efficiency. Now let's talk about effect of load. When the load matches the system's optimal condition, the power transfer and efficiency are maximized. If the load deviates from this optimal point, the system becomes mismatched and both power and efficiency drop. As shown in the load plot on this slide, you can see the peak near the optimum point. And about the effect of distance, increasing distance between the transmitter and receiver reduces the magnetic coupling. This means that less power reaches the receiver and efficiency gradually decreases as the gap grows. The distance plot here illustrates this continuous drop. One of the most critical factors in WPT is the operating frequency. WPT systems are highly sensitive to the resonant frequency, the point at which magnetic coupling and energy transfer are maximized. Both power and efficiency reach their peak at resonance frequency. If the operating frequency shifts away from this point, even slightly, power and efficiency will drop significantly. As shown in the plots of this slide, you can see a sharp peak at the resonant frequency, highlighting how important it is to maintain precise frequency control. Therefore, frequency tuning is essential for achieving maximum energy transfer and system efficiency in any wireless power transfer application. In wireless power transfer, or WPT systems, achieving high efficiency depends on mainly two factors: coupling coefficient and the quality factor. The coupling coefficient is determined by the coil geometry and the distance between the transmitter and receiver. As the distance increases, as we showed in the previous slides, the coupling coefficient naturally decreases. At longer distance, quality factor, or Q, becomes the most important parameter for maintaining high efficiency. The quality factor depends entirely on the coil design, including conductor widths, spacing, and overall geometry. In these figures shown on this slide, the coil designs were optimized by adjusting trace spacing and widths. These improvements reduced losses and increased the quality factor. Additionally, The advanced designs help to reduce skin and proximity effect, further enhancing the quality factor and allowing more efficient power transfer. Now let's simulate one wireless power transfer system inside EMWorks EMAG, the 3D geometry simulation using finite element method. This is a simple geometry of the coils and the dimensions and power rate selected in a way to be near the nominal powers of wireless chargers for electrical vehicles. In this webinar, we just show simple steps and the results of the simulation, but we have a comprehensive step-by-step tutorial of how to simulate different studies like magnetostatic, AC magnetic, and transient simulation of WPT systems. You can find the link of those tutorials inside the description. In this webinar, we just show some practical points like why we selected the conductor widths differently when they get near to the center. You can see the wire diameter or width of the wire in the center is smaller than the wires at the edges. The distance between the wires can be a parameter to modify the quality factor too. If you want to simulate the system from the beginning, EMWorks EMAG has a powerful CAD tool powered by Autodesk Inventor. You can draw the 2D sketch and then use the 3D features to create your parts. All the features of Autodesk Inventor available here, but if you're not experienced in using CAD tools, don't worry, you can easily import any geometry from the other softwares, the native files, or different file extensions like IPT, step file, IGS file, and many other CAD files. You just need to import the file and start the simulation on that geometry. For this project, we only have 2 coils made from copper and outer air. So we don't have any ferromagnetic or back iron for this simulation. I used 2 types of studies, AC magnetic and transient simulation for this project. At the first step, I used the AC magnetic to calculate the inductances of the coils to be able to calculate the resonant frequency. As we talked, if you want to increase the quality factor and the available power transfer, the circuit should work at the resonant frequency. To extract these inductances, mutual inductance and self-inductance of the coils, I created a AC magnetic simulation at the frequency of 85 kilohertz, which is a standard frequency for electrical vehicle chargers. So at this fixed frequency, with having the inductances, we can calculate the relative capacitor to make a resonant circuit. Setting the excitation is pretty easy too. As I mentioned, you can find the details in the tutorials, but to just have a slight review, each of these coils are excited by selecting the geometry, selecting the input and output ports. If I show the preview, it will show how we excited the cross-section of this coil. Let's reduce the preview size. We selected the cross-section of the conductor at the beginning and at the end of the coil. And you don't need to extend the winding to the edge of simulation to be able to excite them. You just need to select the input and output port, and it's not necessary to have a closed loop or connect the windings to the edge of the outer air. With this AC magnetic simulation at the fixed frequency, we extracted just the inductances. And with calculating these 13 microhenry with the excitation frequency, we found that we need 270 nanofarad capacitor to make a resonant circuit. So in the next simulation, instead of exciting the geometry with just injecting current, we used this analysis coupling and we coupled this circuit to the windings. As you can see, for the primary, we injected the current source with 100 ampere value, and we seried this 270 nanofarad capacitor with each of these windings. The primary winding is connected to the current source, but the secondary winding is just connected to the compensator capacitor and a resistance as a load. To maximize the transferred power, I selected the resistance as only 1 ohm. And after the simulation, let's have a look on the results. We can have two different kind of results. Result tables like the energy calculated, flux linkage values, current values. Look at this current value that we injected 100 ampere as the input, and the output has almost 100 amperes too, but in the imaginary part. So it shows that the input current and output current has 90-degree phase shift. We can see the induced voltage too. The induced voltage has the same value. It is almost 700 volts. And the software will calculate the resistance of the coils automatically due to its geometry. The inductances that we saw before this simulation and leakage inductance, impedance, coupling coefficient, resistance matrix, and losses can be calculated too. In the first coil and second coil, we almost have 30 watt copper loss, and it is almost negligible in comparison with the power that can be delivered in 100 amperes that is connected to 1 ohm resistance. The transferred power due to this current and the resistance load is almost 10 kilowatts. That is a nominal power for many types of wireless power chargers for EV. The other kind of results that we can get is flux density and current intensity. Let's have a look on magnetic flux density distribution. Before we plot the magnetic flux, let's first show the air, but in a transparent way. Now in the simulation tab, we can plot magnetic field density in vectors. If you zoom in, you can see the flux distribution from the first coil to the second coil. And a very useful option that you can use inside the field plots is this cross-section option. Without drawing additional surfaces, you can plot any fields in all possible cross-sections. You just need to select the cross-section surface like XY plane or XZ plane or YZ plane, and with the mouse button you can select the place of that cross-section to be plotted. With using this option, you can plot the field in any desired surface. We plotted the field density. Now let's have a look on the current density. In the current density, I don't want to plot a section view. I just need a fringe plot without any sectioning or clipping. As I selected the whole geometry, it plotted the current density in the air too, so of course it is 0. To remove the air from the field plot, you just need to click on component visibility and remove the air. Now let's have a look on the current density distribution on the coils. You can plot the real or phasor plot of each field when you are simulating AC magnetic. I will change the phase to, for example, 35 degree to see the result on both coils. In the first step, we didn't have any current inside the second coil, but as the phase increases, it shows the current density values on the whole geometry in that phase. In 90 degree, as we injected the sinusoidal waveform inside the first coil, the value of the current will be 0. But in 45, I think the values should be almost the same. With plotting current density, you can find the hot spot, the places that you need to change the diameter or distance between coils, and you can measure the skin effect or proximity effect in the windings. The main simulation in this project is this AC magnetic simulation, as it is faster and needs fewer computational resources, but you can do the simulation in time domain too. Transient simulation is possible for this geometry too. Due to the frequency, we use 32 microseconds as the end time and 1 microsecond as the time increment. To simulate the geometry faster, you can increase the maximum logical cores to use. Without any HPC license, you can increase the number of cores up to 32 cores if your computer has the resources. Again, all the results table and fields are available in this simulation too, but this time in the time domain. Let's just plot the magnetic field intensity in this time and use the vector plot. This time, instead of changing the phase of the plot, we can select the step time and observe the results in different time steps. Again, all the vector plot and cross sections are available in the field plot of this analysis too. It was a really simple geometry and sample project for checking the WPT systems, and with the features that the software has, you can model any complex geometry and system and extract the results too. Now, if you have any question, feel free to type it in the comments, and I'm here to answer them all. Thank you.